series on differential equations for undergraduate students. Today's topic is Introduction. The first question arises, what do we mean by differential equations? Before answering this question, let us try to remember one thing which we have already done, the exponential function. Yes, e to the power x. We know that this function has a property that if we differentiate it with respect to x, we get the same function, that is dy over dx is e to the power x. Thus, we got a relationship that dy over dx is equal to y. This relationship is called differential equation. So, now we are ready to answer what is a differential equation. A differential equation is an equation involving an unknown function and its derivatives. Thus, dy over dx is equal to ky, d2y over dx square plus 4y is equal to 0, 1 plus dy over dx square whole to the power 3 by 2 is equal to c times d2y over dx square, x times dy over dx whole square minus y times dy over dx plus x is equal to 0, x times del u over del x plus y times del u over del y is equal to 2u, del 2y over del t2 is equal to c square times del 2y over del x2 are all examples of differential equations. In these examples, we have seen that some involves ordinary derivatives while some examples involve partial derivatives. Thus, we categorize our differential equations into ordinary differential equations and partial differential equations. An ordinary differential equation is an equation that contains one or several derivatives of an unknown function of one variable only. Thus, in our example, the first example dy over dx is equal to ky, the second example d2y over dx2 plus 4y is equal to 0, 1 plus dy over dx whole square complete power 3 by 2 is equal to c times d2y over dx2, x times dy over dx square minus y times dy over dx plus x is equal to 0 are all examples of ordinary differential equations. Here we do have the unknown function y and its derivatives, and the function y was of only one variable and we had the ordinary derivative with respect to that variable only. Now, a partial differential equation is an equation involving an unknown function of two or more variables and its derivatives with respect to independent variables. Thus, in our examples, x times del u over del x plus y times del u over del y is equal to 2u, del 2y over del t2 is equal to c square times del 2y over del x2 are examples of partial differential equations. Here in the first example, u is a function of two variables x and y and the equation involved is partial derivative with respect to x and y. While in the second equation, y is the unknown function and this function is of two variables t and x and it involves the second order partial derivative with respect to these independent variables. Thus, we have seen that all these equations are involving a function of one or more variables, the derivatives ordinary or partial, again the derivatives of first order or higher order, again the derivatives may be having the exponents. Thus, we are now ready to give some basic terminology of the differential equations. The first one is order. The order of a differential equation is the order of the highest derivative of the unknown function involved in the equation. Thus, in our example, let us see First example, dy over dx is equal to ky. This involves the first order derivative only. Thus, the order of this equation is 1. While as the equation d2y over dx2 plus 4y is equal to 0, this involves the second order derivative, and that is the highest derivative involved in this equation. Thus, order of this equation is 2. Similarly, in this equation, 1 plus dy over dx square whole to the power 3 by 2 is equal to c times d2y over dx2. In this equation, it involves the first order derivative as well as the second order derivative. So, the highest derivative involved is the second order derivative. Thus, this equation has order 2. Now, we see in the last example that x dy over dx square minus y times dy over dx plus x is equal to 0. We see the derivatives involved are only of the first order. Thus, order of this equation is 1 only. So, this equation is also being called first order equation. The second term is degree. The degree of a differential equation is the exponent of the highest derivative occurring in it after the equation has been rationalized with respect to derivatives. Let us understand this more clearly with the help of examples. So, in our first example, we do have that the derivative involved is only that highest derivative is first order and its exponent is 1. Thus, the degree of this equation is 1. In the second example, the derivative which is involved, that is second order derivative, is the highest derivative and its exponent is 1. Thus, this equation also has degree 1. Now, see, in this example, we do have that derivative involved is of first order only, but we see that dy over dx has a exponent 2. So, the highest exponent is 2. Thus, degree of this equation will be 2. Now, let us see one more example we had in our examples, that is 1 plus dy over dx square whole to the power 3 by 2 is equal to c times d2y over dx2. In this equation, we do have a power as 3 by 2, that is, it is involving a square root. Now, this is not called a rational equation, because here the power of dy over dx is having 1 over 2 something. So, we will rationalize it. How we will rationalize it? We will square this equation on both the sides, and thus we would get 1 plus dy over dx square whole to the power 3 is equal to c square times d2y over dx2 is equal to dx2. Here the highest derivative involved is the second order, that is d2y over dx2, and its exponent is 2. Thus, degree of this equation has 2. Now, we can categorize the equations in different manners. So, one more categorization of differential equations is coming as linear differential equation. A differential equation is called linear if the function and its derivatives are appearing in the equation with degree 1 only and separately. If this is not happening, then it is called non-linear. Let us understand this more clearly with the help of examples. So, first let us see the example of linear differential equation. See this example, x cube times d3y over dx3 minus 3x square times d2y over dx2 plus 6x times dy over dx minus 6y is equal to 0. Here we see that the derivatives involved are first order, second order and third order, and all these derivatives and the function y are in degree 1 only. None of them have any exponent. Moreover, none of the places I do have that the function and derivatives are appearing simultaneously in any component. Thus, this equation is linear in the unknown function y and its derivative. This is called a linear differential equation. Let us see one more example. d2y over dx2 minus y is equal to 0. Here we do see is that is the derivative is d2y over dx2 and y both are occurring in degree 1 and separately. Thus, this is also an example of linear differential equation. Let us see some example of non-linear equations. See this first example, d3y over dx3 plus 2 times d2y over dx2 multiplied with dy over dx plus x square times dy over dx whole to the power 3 is equal to 0. Now, we see here that derivatives are coming with exponent as the first derivative dy over dx has degree 3, while as in the second component d2y over dx2, that is the second order derivative and the first order derivative are occurring simultaneously. Thus, this is a non-linear equation. The second example, d2y over dx2 minus m times 1 minus y square times dy over dx plus y is equal to 0. Here we see that derivatives are occurring in the first degree only, but the function itself is occurring in the second degree. Moreover, in one component we do have that the function and its derivative are occurring simultaneously. Thus, this is also an example of non-linear differential equations. Let us have something more about linear differential equations. A linear differential equation of order n is a differential equation which is written in the form a n x times d n y over d x n plus a n minus 1 x times d n minus 1 y over d x n minus 1 and so on, a 1 x times d y over d x plus a naught x times y is equal to f x. We see here that all the derivatives are occurring in first degree only and their coefficients are the function of x only, none of them involve the y or its derivative. This is a linear equation. Now, here the highest occurring derivative is dny over dx and that is nth order. Thus, order of this equation will be n only if its coefficient a n x is not a 0 function. Thus, this equation will be called a linear equation of order n if a n x is not a 0 function. Why? If a n x is a 0 function, the first term will not be there and then the highest derivative would be only d n minus 1 over d x n minus 1, that is n minus 1th order. So, this is a differential equation of order n. Many times this kind of equations are also being written as a n x times y n plus a n minus 1 times y n minus 1 and so on, a 1 x times y 1 plus a naught x y is equal to f x. What the change we have done here, if you see, is that we have replaced this y n with d n y over d x n. That is the nth derivative, we have used another notation y n. Similarly, for n minus 1th derivative, we have used the notation y n minus 1 and so on for second derivative the y 2 and for first derivative y 1. These notations are being used so that it is convenient in writing. So, this is also one way of writing the differential equations and these notations are being used for convenience. Now, we have seen that these differential equations are functions and their derivatives and their relationship. Thus, a function will satisfy these equations. So, any function which is satisfying these equation will call its solution. So, now we come to another term, solution. A function is said to be a solution of a differential equation if the function and its derivatives when substituted in the differential equation satisfy the equation identically. Let us try to see it with the help of example. Let us take this equation x times dy over dx is equal to 2y. We can check that y is equal to x square. This is a solution. How can we check? Let us see, that is for y is equal to x square, what will be dy over dx? That will be 2 times x. Now, this value of the function, that is x square, and its derivative 2x, we can put into the given equation, and thus what we will get, x times x is equal to 2x square, and right hand side is also 2x square. Thus, we get that this equation is being satisfied identically. Thus, what we got, that x square is a solution of the differential equation x times dy over dx is equal to 2y. So, we have got a solution. Now, let us see what, as soon as we talk about solution, the question comes existence and uniqueness. What do we mean by existence? Does a differential equation has a solution? The answer to this question is called existence. Then it comes uniqueness. Does a differential equation has more than one solution? If yes, can we find out a particular solution? That is, if yes, how can we find out a solution which satisfies a particular condition? So, now we have seen that a differential equation may or may not have a solution. If it is having a solution, it may have more than one solutions. So, now we are going to categorize the solutions also. The first categorization is general solution. The description of all solutions to differential equation is called the general solution. Let us elaborate it little bit more. We have just seen this example, that is x times dy over dx is equal to 2y. Now, let us see little bit more. If I take this function c times x square, we can check that this is also a solution of this equation for all values of c. We can check it. See, y is equal to cx square, the dy over dx will be 2 times cx. Now, if I incorporate these things into the equation, what I would get is that x times 2 c times x is equal to 2 cx square, which is nothing but the right hand side. Thus, cx square is also satisfying this equation for all values of c. What it says, that is, we are getting not only one solution, but many solutions, that is, for each value of c I will get one solution. So, this cx square will be called the general solution of this differential equation. Now, the second question is uniqueness. Before answering this, let us try to define something more over here. Initial value problem. A problem in which we are looking for the unknown function of a differential equation, where the equation of unknown function and its derivatives at some points are known, is called initial value problem. This is also referred as IVP in short. Say, for example, the equation x times dy over dx is equal to 2y. If I incorporate one extra condition, that the function value is 5 at x is equal to 1, this is called an initial value problem. A solution to the initial value problem is known as particular solution. So, now let us see this with the help of example. Just now we had seen that y is equal to cx square is the general solution of x times dy over dx is equal to 2y. Now, incorporate this condition, that is y at 1 is 5. That means, in cx square at x is equal to 1, we will put what we will get is that c is equal to 5. Hence, we got that y is equal to 5x square is a particular solution. This solution we have got when we have used this initial condition, that is, the function value is 5 at x is equal to 1. Let us understand it little bit better with the help of graph. We see here is, that is, this is the graph of all the y is equal to cx square. Here these graphs I have made for different values of c, that is, all these functions are solution to the differential equation x times dy over dx is equal to y. For different values of c, we are getting it. Now, in our condition, what the initial condition was given, that at x is equal to 1, the value of the function should be 5. We see is that is at 1. If we see here, we are getting the value of 5. So, this is the graph which we will be, or this is the function which is coming as a particular solution. We see is at 1, no other function has value 5 over here. So, thus to arrive to a unique solution, we require a particular condition. Now, we have started this lecture with this function, that is exponential function, and we had seen that this is satisfying the equation dy over dx is equal to y. Now, let us take another differential equation, dy over dx is equal to 2y. This is closely related to the previous one. The only difference is of a constant 2 we have used at the y. But now, this e to the power x, this does not satisfy this equation anymore. Now, how to find out the answer to this equation, that is which function will satisfy this equation? Okay, let us take this assumption that the function should be of the same form, that is exponential one. We have to do little bit experiment with the same function. So, let us assume that we take a function c times e to the power kx, where both this c and k are constants. If I differentiate it, we get dy over dx is equal to k c times e to the power kx, that is k times y. Thus, we have got that function y is equal to c times e to the power kx satisfies the equation dy over dx is equal to ky. So, we had started with dy over dx is equal to 2y. So, now what I will do? I will replace this k by 2. So, we got that c times e to the power 2x is solution to the differential equation dy over dx is equal to 2y. Now, what we have actually got, let us summarize the result. We have actually got that c times e to the power kx is a solution to the differential equation dy over dx is equal to ky. This is true for every value of c. So, thus what we have got, actually we have got a general solution to the differential equation dy over dx is equal to ky, where this constant k is determined by the equation. As in our example, what we have chosen? We have chosen k is equal to 2. This k is also referred as rate constant, but this c is not determined by the differential equation. That says, we have actually find out a whole family of possible solutions, and one for every possible value of this constant is a solution. Let us see the graph of this function. This is the family of exponential curve. So, here I have made this, you see is that is here we have different exponential curve, all these are e to the power 2x functions, but with different values of c. So, all these functions satisfy the equation that dy over dx is equal to 2y. How do we choose any particular solution? That says, we require something more for that one. What that more? Let us see is that we say is that from where this function is starting, that is what is the initial value. So, suppose I say is that is my initial value, that is y at 0, that is initially is 1. Now, if I get what is the solution, that c times e to the power kx, that will be actually 1. Thus, what we get, that c is equal to 1. If I replace c is equal to 1, I will get this function. We see that this function, we are initially at 0, we are starting at 1. Thus, we are having this as a function which is satisfying this particular condition. So, if we change our initial condition, say the function is starting at half, we will get that a different function, that is we will get here y is equal to half times e to the power 2x, this curve. Now, if I change my initial condition to minus half, that is the function is starting at minus half, we see that our function solution has been changed. So, thus what we have got, that we summarize the result, that we have got the initial condition is picking up a particular solution. The differential equation gives me a whole lot of general solutions. So, now I give you some question to think about. Find the solution to differential equation dy over dx is equal to minus 5y. Use the initial condition that at 0 the function is starting with 10. See, that is how the graph of this function will look like and what is the difference it has with our example just now what I have done. Okay, moreover, you can experiment little bit more. See that if you change the initial value to 0, that is the function is starting to 0. Now, find it out what you are getting. Does it drastically change your solution? Think about it and then see. So, here are some more questions for you to think about. Find the general solution to the differential equation dy over dx is equal to 2x. Think about what should be the solution of this differential equation. Second question is dy over dx is equal to 3. What will be solution of this differential equation? Moreover, use the initial condition that y0 is equal to 2 in both these questions and find out a particular solution. You can experiment with other initial conditions also and see what you are getting. This would give you a little bit insight, that is what we mean by differential equation and its solution. So, we have learned what are differential equations and what are solutions of differential equations. Now, the question arises, why do we study differential equations, or what we achieve by knowing the solution of differential equations? In other words, what is the application of these differential equations, where in real life we will apply this differential equation, so that we do study these differential equations. That says, that is what is application of differential equation. The answer is modeling. What is modeling? Modeling is that actually transforming the physical phenomena into mathematical formulation. By changing physical phenomena into mathematical formulation, we do know more about that phenomena. Moreover, we may predict the future behavior of that phenomena. Thus, differential equations are very important topic in mathematics, science and engineering, in all those situations where changes occur and predictions are desirable. The most of the systems which come under study, they observe certain natural laws or observations. These physical changes, when we transform into the language of mathematics, may turn out to be differential equations. Thus, we try to see which kind of functions or which kind of phenomena will translate into differential equations. A typical real world application of differential equations involve those phenomena which changes with the time and the change is proportional to the rate of the change or the acceleration of the change. That is, whenever these relationship we can use as the differential equations. Now, whenever a physical law involves a rate of change of a function such as velocity or acceleration etc., we do get differential equations. Thus, in physics and engineering application we do get many differential equations. An example here I have taken. Here there is a stationary object which is initially at initial position. A force is being applied on it and this stationary object starts moving. So, from where it starts moving, that point I am taking initial position. After time t1, it reaches to a position x and it is still continues to move, and at time t2 it reaches to position y. We have observed here that this object is not covering equal distance in equal time, or in other words, the equal distance has not been covered in equal time. That says that the movement of the object, that is the velocity of the object, was changing. And why it is happening? Since the force has been applied once only and object is moving on certain surface, that surface is also giving some force, so this velocity is changing. Now, this is an example where we can say that we can use the differential equation. See, for simplicity, if I use that the change which is occurring is at constant rate, that is the distance it is covering with respect to time, that is changing with constant rate. So, if I denote this distance by s, then ds by dt is a constant, say a, and this thus we have got, that is the change in the distance is at constant rate. This is a differential equation, and by solving this we can predict that at time t3 where this object will be. This is what very simple application here we do have. So, now in this application what we have done? We have taken one assumption that the change is at constant rate. Thus, we have got that everyday problem what scientist is struggling is how do I translate a physical phenomena into a set of equations which can describe it. In real world, actually it is not possible to find out a system of equations or a set of equations which describe this phenomena completely and adequately. So, what we do is we find out a set of equations which can describe this system approximately, and when we say is approximately, of course, we are making certain assumptions, certain observations, and thus we come up with some set of equations, we try it, we see that how it is working, we compare it with real world results, and then again we can improve upon our set of equations. This is what is the modeling we are having, and in all those situations where changes are occurring and we want to find out how these changes are happening, all these are coming modeling through differential equations. Now, let us try to see this with a simple example. The first example is about the population growth. We are writing it as unlimited because we had made an assumption that there is no condition or no control on the growth. The example is the number of bacteria in a liquid culture is observed to grow at a rate proportion to the number of cells present. At the beginning of the experiment, there are 10,000 cells, and after 3 hours, there are 5 lakh cells. Now, how many will be there after 1 day of growth if this unlimited growth continues? What is the doubling time of bacteria? Now, let us start with this example. What we have been given, that is a liquid culture is having certain number of cells and it is growing with time. Now, how do I translate it? You see here, first we will assume that is from the starting of the experiment, the time elapsed that will denote by t, and the time we will be counting here in the hours. Second thing we would be assuming is the unknown function y, that is the number of cells at time t. Why we are calling it a function? Because it is changing with time t. Then what we have been given? We have been given that the starting of the experiment, the number of cells are 10,000, that is y at 0 is 10,000. here I have used another notation y naught. We will see that is, this is also we are sometimes referring, that is the value of the function at that point. Now, what more we are being given in this one, that is the rate at which this growth is taking place, or that is the number of cells are changing, that is called the growth rate. So, what will be the growth rate? Growth rate will be dy over dt. This is given that it is changing according to the size of the population at that time t. That means, it is given that dy over dx is equal to ky, where k is the constant of proportion. Now, we do remember this equation. We have seen this equation in our first part of this lecture. We do know that this equation has a solution as yt is equal to c times e to the power kt. Now, we are being given initial value that the starting of the experiment, we do have y at 10,000 cells. Now, if I incorporate this initial value, we have seen in our first examples, that is, this should be c. So, c would be 10,000. Thus, what we have got, that this function would be 10,000 times e to the power kt. Now, the question is, what will be this k? For that, we have to see our experiment a little bit more. We are being given that after 3 hours, it has been observed that the number of cells are 5 lakh. So, now translate this into the mathematical formulation. We are being given, so at t is equal to 3, my function would be 10,000 times e to the power 3k. It is given that number of cells at that time are 5,000. So, if I equate these two things, what I do get, e to the power 3k is equal to 50. Now, we can solve this to find out the value of k. How we will solve it? We will just take the natural logarithmic on both the sides of this one. So, we do get log of e to the power 3k is equal to log of 50, which is giving us that 3k is equal to log 50. Thus, k is equal to log 50 by 3, and now we will incorporate the value of natural logarithm of 50, which is approximately 3.91. Thus, we are getting the value of k as 3.91 by 3 is equal to 1.3. So, what we have got, that is the value of k is 1.3. Now, this is the rate constant, and what rate we would have, because we have taken our t as the time in hour. So, it would be that it is changing 1.3 per hour, that is rate of change is 1.3 per hour. So, now what is our solution? We have got that at the time t, the number of cells will be 10,000 times e to the power 1.3 t. That is, this is we have got this function as a solution, or this is what we are giving as the number of cells at the time t. Now, let us see this by the graph. We see that is, this is the graph of the function e to the power 1.3 t, and since initially we have started at the value 10,000, we see here in the graph that it is 10,000 is starting. So, this is the solution of this one. Now, we are ready to answer the question, that is, what will be the growth after 1 day, that is after 24 hours. That is, we will incorporate t is equal to 24 in our solution. What it will be? 10,000 times e to the power 1.3, and in place of t I will put 24, which we will when solve will reach to 10,000 times e to the power 31.2, which will be giving me 3.5 into 10 to the power 17. That is, these are the number of cells at the end of 1 day at the time of 24 hours. Now, let us try to solve the second part of the problem, that is, what is the doubling time of the bacteria. So, first we should know what is the doubling time. Doubling time is actually the amount of time one takes for a given population to double in size. So, let us explain it. Let us say that is tau is the doubling time. Then what we are being said is that is the number of cells at time tau, that is y tau, should be twice the number of cells at the initial position, that is y naught. So, now incorporate these information in our solution, because we do know what is the yt. Y tau is 10,000 times e to the power k tau, and initially the value of the y naught, that is the number of cells at the beginning, are 10,000. So, twice of this would be 20,000. Thus, what we got, that e to the power k tau is equal to 2. Now, we do know that in this solution that k is 1.3. So, we incorporate this k tau is equal to log 2 after taking logarithmic and incorporating the value of k as 1.3, we do get that tau is equal to approximately 0.69 divided by 1.3, that is approximately 0.533. What is this? This is tau, that is the time, and time how we are measuring? In hours. So, this is doubling time is approximately 0.533 hours, which if I change into the minutes, I do get approximately 32 minutes. So, we have here one problem where we are interested to know the growth of bacteria in a liquid culture. We had observed that experiment for certain time. We had initially started our observations when there were 10,000 cells, and after 3 hours we have observed that there are 5 lakh cells. And one more assumption we have made, that the growth is proportional to number of cells present in the culture at that time. With the help of these 3 things, we have modeled our problem. We said since the rate is changing according to the size of population, we got the equation dy over dt is equal to ky, and we have solved that equation with the help of other observations which we have made. The first observation, that initially we have started at 10,000 cells, then the fact that after 3 hours we have observed it as 5 lakh. From there we have got the rate constant, that is k, and then we could predict it, that is after 24 hours how many bacteria will be in that culture. Moreover, we can also answer the question, that is in how much time the population will get doubled, and these answers we have made. Similarly, let us see one more example of the similar nature, but little bit different, that is radioactive decay. Radioactive decay is a property which characterizes the substances whose atoms undergo spontaneous changes. These are being stored either in radioactive isotopes or in that are unstable forms, or in stable form on those materials which decays. These decays are normally at a constant rate, which when they burst are being counted on a Geiger counter. Thus, these bursts are being, that is atoms are being burst at a constant rate, and this isotope, that is the radioactive material, changes to the stable material. That says is that this constant rate would be proportional to the number of atoms present at the isotope at that time. So, this decay is, that is the change in the mass of radioactive material is proportional to the mass present at that time, and this would be decreasing. We can understand this in another words, as if example, if there is half of the material present at the isotope, then the number of bursts in the atoms will be half of the times whatever it is previously. Thus, this change is in the decreasing order, and this is called decay. Now, this problem also we can study as we have used this growth phenomena. what is the difference between the growth phenomena and this decay phenomena? Is the thing is that is there the things were changing to, they are growing up, and here the population is decreasing or decaying one. So, we can use the same kind of thing what we have been given, that is, let us see, we have been defining the variable here first, that is t is the time, and let us say mt is the variable, that is the mass of the radioactive isotope at time t. It is given that this mass is changing at a constant rate which is proportional to the mass present at that time, that is the rate of change of the mass would be dm by dt. This is proportional to the mass given at a time. Thus, we can say that dm by dt is equal to minus km. Now, see, here I have used minus sign. Why? Whatever be the mass present at the isotope, that will always be a positive number, that will be always a positive, and it is decreasing. K I have used as a positive constant. So, I have to use the sign minus, because as the time is changing, the mass is decreasing. So, the rate of change should be negative. Thus, we have used here minus k, and this solution of this differential equation, now we have already seen this kind of differential equation. The difference is here, that is rather than having plus k, we are having here minus k. Of course, we have changed the variable from y to m. So, the solution would be, that is in the solution itself also we would change it to the minus k, and the solution would be that mt is equal to m naught times e to the power minus kt. Here m naught I have used as the constant, or that is the constant in the general solution instead of c. Why m naught I have used? Because there must be some initial value known for this experiment also, that is from where we are starting observing this isotope to decay, that is that m naught is initial mass present on the isotope. Now, we are ready to solve a problem. Let us see that is what is this problem. Before going to the problem, let us see this function little bit more. Since this function is negative exponential, it is having, see, we have this function which is decreasing. Of course, this function should be decreasing, because what we are having is that solution must be a mass which is a function which is decreasing, and we see as initially we are starting at different values, we do have different solutions. Now, try to solve one problem. Let us see what the problem we are going to solve here. Carbon 14 is a radioactive isotope of carbon that has a half-life of 5600 years. It is used extensively in dating organic materials that are very old, sometimes thousands of years of. So, the question is, what fraction of original amount of carbon 14 in a sample will be present after 10,000 of the years? Now, let us see is that how we are going to model this problem. Carbon 14 is a radioactive isotope. So, it has a property that it will decay, and the decay would be at a constant rate, and that rate would be proportion to the amount of the radioactive material, that is carbon 14 present at that time. Thus, the equation we will have is that dm by dt is minus km. We have already seen that the solution of this equation is m naught times e to the power minus kt. Now, for this problem we have to find out what is m naught and what is k, or to answer this we have to know is that is after 10,000 year what will be the fraction of amount which will be left. That is, we are not necessarily want to know what is m naught, whatever be m naught after 10,000 years, what fraction of that amount will be there. So, we are more interested in finding first what is k. How we are going to find it out? We will see in our example what other conditions are given to us. We have been given this information that half-life. Now, what is the half-life? half-life of a substance or a decaying material is the amount of time it takes for 50% of the original amount of the substance to decay. We have been given here that half-life of this is 5600. So, let here tau be the half-life, that is the tau will be the time it will take for material to come as the half of that percentage, and let us say that m naught is the amount of the substance present initially. Then what it will give? Now, because we do know what is that solution, that is mt is equal to m naught times e to the power minus kt. We have been given that at tau is equal to 5000. So, at tau I would get m tau as half times of m naught. Now, put tau as 5600 in our solution, and we do get that m naught times e to the power minus k tau as half m naught, or e to the power minus k tau as half. Thus, what we are getting is that 2 is equal to e to the power k tau, and thus tau is log 2 upon k. So, we are just solving this equation without actually incorporating the value of tau. We are given that tau is equal to 5600. So, we will incorporate this and we get k is equal to log 2 upon tau, which is 0.69 divided by 5600, which gives approximately 1.2 into 10 to the power minus 4 per year. That is the time we have incorporated here in the terms of year, because it takes a long time. So, we have got that k is equal to this. Thus, what we have got the solution? We have got the solution as mt is equal to m naught times e to the power minus 1.2 times 10 to the power minus 4 t. Now, we are ready to answer our question. Question is that after 10,000 years, the fraction of the original amount will be m at 10,000 divided by m naught, because initially the amount is m naught. So, now use these informations in our solution. M at 10,000 will be m naught times e to the power minus 1.2 into 10 to the power minus 4, and at the place of t I will use 10,000, which gives me that it is e to the power minus 1.2. Now, we can calculate this value, which is coming up approximately as 0.3. What does it says? After 10,000 years, the 30% of the original sample will be left on the carbon 14 isotope. That is again we have seen here in this one, that if we are talking about a decay which cannot be stopped by any outside source. So, we are having the decay is happening, and that decay is again at a constant rate, and that constant rate is proportional to the population size or the material present at that time. That again we have used the same kind of differential equation, and we have solved this problem also. So, in both these examples, we have seen that we have used the exponential function and its differential equation. So, that is why I had used this example, just because I have started my lecture with exponential function. So, this is not the only application of differential equation. Actually, we can model many kind of physical phenomena, all those phenomena where changes are taking place, and we are interested to know what will be the future behavior of that phenomena. So, wherever this changes are occurring, we do have the differential equations. Knowing the differential equations, knowing that how to solve those differential equations, we can know the function, that is we can know that phenomena, what this phenomena is. The function says is that if I say this is a function, it says is I do know completely about this thing. So, if any phenomena I am saying is a function, I do completely know the phenomena. I do know the characteristic of that phenomena. I can predict the future behavior of that phenomena, or I may actually calculate many things about many characteristics of that particular phenomena. That is why these differential equations are very, very important. Here I would conclude today's lecture.